Hello. In the next couple of episodes, we will talk about symmetries and group theory in quantum mechanics. We observe that the laws of physics are the same in different places on Earth and presumably at different places in the universe. This is spatial invariance. The laws of physics are the same at different times. We call this time invariance. And they're the same irrespective of what we call up or down, left or right, irrespective of how we orient ourselves in our coordinate system. This is orientational invariance. These symmetries must be reflected in the equations or laws of physics. Thus, in classical physics, we have Newton's equation, force equals mass times acceleration, and this equation is invariant under spatial translation. If we change x to x dash, which is x plus delta x, through any interval delta x, and thus even for continuous translations through an infinitesimal interval delta x, the equation is invariant. Likewise, Newton's equation is invariant for time translation, that is t substituted with t dash equals t plus delta t through any time interval delta t, and thus even for continuous translation through infinitesimal time interval delta t. And it's invariant to spatial inversion. If we change x to x dash equals minus x, the equation has the same form. And it's invariant to time reversal. If we change t to t dash equals minus t, again the equation is invariant. In quantum mechanics, we have Schrodinger's equation h psi equals ih cross del psi by del t, which gives psi at time t equals psi at time 0 times e to the power minus iet by h cross, and this is likewise invariant under translation, inversion, time translation, and time reversal. For example, for time reversal, if we substitute t with t dash equals minus t, we have psi going to psi dash, which is psi at time minus t, which is equal to psi at time 0 times e to the power plus iet by h cross. And h goes to h dash, which is equal to minus ih cross del by del t. Psi dash is an eigenfunction of h dash, just as psi is an eigenfunction of h with the same eigenvalue e. Emmy Noether brought out the relation between continuous symmetries and conservation laws. Noether's theorem can be stated as: if a property of a system has a continuous symmetry, then there are corresponding quantities whose values are conserved in time. We can also state Noether's theorem in the form: every differentiable symmetry of the action of a physical system has a corresponding conservation law. So the action is given by the time integral of the Lagrangian, where the Lagrangian is the kinetic energy minus the potential energy. This theorem was proved by mathematician Emmy Noether in 1915 and was published in 1980. Writing the Lagrangian as a function of the generalized coordinates q, the generalized velocities q dot and time, that is L of q dot and t equals half m q dot squared minus v. The momentum becomes p equals del L by del q dot, which is equal to m times q dot, that is mass times velocity, which gives the Euler-Lagrange equation d dt of del L by del q dot equals del L by del q, or p dot equals minus del v by del q, or force is the rate of change of momentum. If a physical process behaves the same regardless of place or location, then its Lagrangian has to be symmetric under continuous translations in space. That is, L cannot depend upon Q. That is, del L by del Q equals 0. Substituting this in the Euler-Lagrange equation, leads to the law of conservation of linear momentum. Thus, ddt of del L by del Q dot, which is P dot, is equal to del L by del Q, which as we have shown is 0. Or in other words, P dot equals 0, or the momentum is constant. Thus, the translational invariance leads to the law of conservation of linear momentum. Likewise, it can be shown that rotational invariance leads to the law of conservation of angular momentum. If a physical system behaves the same regardless of how it is oriented in space, its Lagrangian has to be symmetric under continuous rotations. Noether's theorem then dictates that the angular momentum of the system is conserved. The proof follows exactly the same pattern as before, with the generalized coordinate here being the angular coordinate. This holds also for discrete symmetries. Thus, a system with inversion symmetry leads to the conservation of parity. If the behavior of a physical system does not change upon spatial reflection, then its Lagrangian has reflection symmetry, and according to Noether's theorem, this symmetry results in the conservation of parity. Likewise, time translational symmetry gives rise to the conservation of energy. If the behavior of a physical system does not change upon time translation, then its Lagrangian has to be invariant to time translation, and according to Noether's theorem, this symmetry results in the conservation of energy. In electrodynamics, it is easily verified that Maxwell's equations of electrodynamics are invariant to spatial reflection, that is x going to x to minus x, and time reversal, that is t going to minus t. Thus, parity is conserved in electrodynamics. However, parity is not conserved in weak interactions, the force that leads to beta decay. Outside the nucleus, the neutron is unstable with a half-life of around 15 minutes, decaying to a proton, an electron, and an antineutrino by means of the weak force. Chen-Ning Yang and Tsung-Dao Lee received the 1957 Nobel Prize in Physics for their work on parity non-conservation in weak interactions. However, the laws of physics are invariant under the simultaneous transformations of charge conjugation, parity transformation, and time reversal, or CPT. In special relativity, we have Lorentz invariance, that is, for observers in different inertial frames where one is moving with a velocity v along the x direction relative to the other, there is a Lorentz contraction given by x dash equals x minus vt divided by square root of 1 minus v squared by c squared, y dash equals y, z dash equals z, and there is a time dilation given by t dash equals t minus v by c squared times x divided by square root of 1 minus v squared by c squared. The Lorentz group is the group of all Lorentz transformations of Minkowski spacetime. The Lorentz group expresses the fundamental symmetry of space and time of all known fundamental laws of nature. So that brings us to the question, what is a group? A group G is a set of objects together with an operation that acts on elements A and B to form another element, satisfying the following properties. The first is closure, that is, for all A and B in G, the result of the operation AB is also in G. The second is associativity, that is, for all A, B and C in G, AB times C is equal to A times BC. Third, there exists an identity element I in G such that for every element A in G, IA is equal to AI, which is equal to A. And fourth is, for every element A in G, there exists an inverse element in G such that A inverse equals A inverse A equal to I. For those who are comfortable with mathematical notation, those four conditions can also be written in this form. Note that the number of elements in a group is called the order of the group. Let us now talk about symmetry groups in chemistry. A point group is the group of symmetry operations in a molecule. Examples of such symmetry operations include reflection in a plane represented by sigma, rotation about an axis. For example, C2 is a rotation by 180 degrees, C3 would be a rotation by 120 degrees, C4 would be a rotation by 90 degrees, and so forth. Inversion in an inversion center represented by small I. A space group is the group of symmetry operations in a crystal. It is formed by the addition of the discrete translational symmetry of the crystal to the symmetry operations in a point group. The discrete translational symmetry is by an integral multiple of the lattice constant. For example, x to x plus a along the x-axis, y to y plus b along the y-axis, z to z plus c along the z-axis. Examples of such additional symmetry elements generated by this combination are glide planes and screw axes. To give some examples of finite groups, note first of all that there can be no group of order 0 because every group must have an identity element, so the minimum order is 1. The only group of order 1 is the group which has only the identity element. The group with the elements I and A with a squared equal to I is a cyclic group of order 2. Since I times A is equal to A times I is equal to I times I is equal to I, and A times A is equal to I. So the group is closed and every element is its own inverse. Examples of this is the group with the numbers 1 and minus 1 with a multiplication operation. Since 1 times 1 is equal to 1, 1 times minus 1 is equal to minus 1, which is an element of the group. Minus 1 times minus 1 is equal to 1, which is also an element of the group. So the group is closed and it has an inverse, it has an identity, and every element is its own inverse. Likewise, with symmetry operations, the group with I and sigma, a reflection, is a cyclic group of order 2. Since two reflections in the same plane bring us back to the identity, therefore the group is closed and every element is its own inverse. Similarly, the group with I and C2 is also a cyclic group of order 2, since two rotations through 180 degrees around the same axis brings us back to the identity. So the group is closed and every element is its own inverse. The group with C3 squared and C3 cubed equal to I is an example of a cyclic group of order 3. C3 is a rotation through 120 degrees. C3 squared is two such operations performed one after the other, or a rotation through 240 degrees. And C3 cubed is a rotation through 360 degrees, which is the identity. I is its own inverse, whereas the inverse of C3 is C3 squared, and the inverse of C3 squared is C3. Likewise, the group with the elements plus I, plus 1, and minus 1 is an example of a cyclic group of order 4 with a multiplication operation, where I is the square root of minus 1. It is easy to check that this group is closed and every element has an inverse. The examples discussed in the previous slide are all cyclic groups, as each of these groups can be written as epsilon, epsilon squared, epsilon cubed, etc. until epsilon n, which is equal to I, where n is the order of the group. To take some examples of infinite groups, let me ask, does the set of all positive integers form a group with respect to the addition operation? Why or why not? And what do you need in order to make a group out of this set? And which is the identity element? Well, what you need is you need to add 0 and all the negative integers also to the group in order that the group is closed. And what is the identity element? The element is 0. Okay, so the set of all integers, positive, negative, and 0, forms a group with respect to the addition operation. 0 is the identity element, and the inverse of the element x is minus x, because remember we are talking here about the addition operation. Okay. Does the set of all integers form a group with respect to the multiplication operation? Again, why or why not? And what do you need in order to make a group out of the set? Well, what you need is that you need to add the fractions also in order to ensure that the group is closed. Which is the identity element? The identity element is 1. Okay. So the set of all rational numbers excepting 0 forms a group with respect to the multiplication operation. 1 is the identity element, and the inverse of x is 1 upon x. Let us now take some theorems. The inverse of a product of two or more elements is the product of their inverses in reverse order, just as with operator algebra. That is, the inverse of ABC is equal to C inverse, B inverse, A inverse. It is easy to prove that the order of any subgroup of a group is an integer divisor of the order of the group. Note that there will always be a cyclic group at any order. In general, the commutation property is not required for a group. A group which has the commutation property is called an abelian group. So the definition is a group where all elements commute with each other is an abelian group. Again, it is easy to prove the theorem that all cyclic groups are abelian. Now we define the conjugate. If A, B, and X are elements of a group such that B is equal to X inverse AX, then B is said to be the conjugate of A, and conversely A is the conjugate of B. A set of all elements conjugate to each other is called a class of the group. I will now state a few more theorems and leave the proofs as an exercise for you. Every element is conjugate with itself, since one can always choose x equals I, so that A equals x inverse AX. If A is conjugate to B, then B is conjugate to A. If A is conjugate to B and B is conjugate to C, then A is conjugate to C, the associative property. The order of a class of a group is an integer divisor of the order of the group. Any element that commutes with all other elements in a group is in a class by itself. We can now form a multiplication table for a group such that each row and each column in the group multiplication table lists each of the group elements once and only once. Thus, no two rows in a group multiplication table may be identical, nor may any two columns be identical. The closure property thus requires that each row and each column in a group multiplication table is a rearranged list of the group elements. Since any symmetry operation takes every set of atoms in the molecule to a new set of coordinates, we can represent every symmetry operation as a matrix operating upon the coordinate vectors of the atoms. A symmetry operation O moves a general point P with coordinates x, y, z to a new set of coordinates x dash, y dash, z dash. Thus, O operating on x, y, z gives x dash, y dash, z dash. The trace, or the sum of the diagonal elements of the matrix O, is known as its character and represented by the symbol chi. Consider the water molecule. The symmetry operations include, first of all, identity, which means do nothing. C2Z, which is rotation through 180 degrees about the z-axis, the axis passing through the oxygen and bisecting the HOH angle. Sigma V XZ, that is reflection in the XZ plane, which is the plane of the screen itself. And sigma V dash YZ, that is reflection in the YZ plane. Each of these symmetry operations maps an atom in the molecule to an identical atom. Thus, the point group includes the elements I, C2Z, sigma V XZ, and sigma V dash YZ. So let us now write the matrix representation for the symmetry operations of C2V. Identity maps XYZ to XYZ. C2Z, the rotation around the z-axis, leaves the z-coordinate unchanged but maps the x-coordinate to -x and the y-coordinate to -y. Okay. Therefore, the matrices for identity are the diagonal identity matrix 1 0 0 0 1 0 0 0 1, and for C2Z -1 0 0 0 -1 0 0 0 1. The trace chi of I is equal to 3, whereas the trace of C2 is equal to -1. Reflection in the XZ plane leaves the x and z coordinates unchanged but flips the y coordinate. Reflection in the YZ plane leaves the y and z coordinates unchanged but flips the x coordinate. So the matrices for sigma V XZ are 1 0 0 0 -1 0 0 0 1, and for sigma V dash YZ -1 0 0 0 1 0 0 0 1. Therefore, the trace chi of sigma V is equal to the chi of sigma V dash, which is equal to 1. The matrix representations make it easy to verify the products of the symmetry operations. First of all, identity times any element is equal to that element itself. C2 times sigma V gives sigma V dash. Sigma V dash times sigma V gives C2. And this is an abelian group, so sigma V times C2 is also equal to sigma V dash, and sigma V times sigma V dash is also equal to C2. And similarly, sigma V dash times C2 is equal to C2 times sigma V dash, which is equal to sigma V. Thus, we have obtained the full multiplication table for C2V. Let us consider one more example, the ammonia molecule, which has a pyramidal structure as shown here, with the nitrogen at the apex of the pyramid and the hydrogens at the three corners of the base. The symmetry operations here are identity, that is do nothing, C3Z, rotation through 120 degrees about the z-axis, that is the axis passing through the nitrogen atom and the center of the triangular base. Okay. Then sigma V, reflection in a plane passing through nitrogen and hydrogen atom 1 and bisecting the H2H3 line. Sigma V dash, reflection in a plane passing through nitrogen and hydrogen atom 2 and bisecting the H1 H3 line, and sigma V double dash, reflection in a plane passing through nitrogen and hydrogen atom 3 and bisecting the H1 H2 line. Thus, the point group consists of the elements identity, C3 squared, sigma V dash, and sigma V double dash. For the point group C3V, it is easy to write the matrices for the identity C3Z, C3 squared Z and sigma V xz. For the identity we have as before 1 0 0 0 1 0 0 0 1. For C3Z we have cos 120 sin 120 0 minus sin 120 cos 120 0 0 0 1, which is minus half root 3 by 2 0 minus root 3 by 2 minus half 0 0 0 1. If C3Z is a clockwise rotation through 120 degrees, C3 squared is an anti-clockwise rotation through 120 degrees. And so we have for C3 squared minus half minus root 3 by 2 0, root 3 by 2 minus half 0 0 0 1, and for sigma V xz we have as before 1 0 0 0 minus 1 0 0 0 1. The traces are for identity equal to 3, for C3 and C3 squared equal to 0, as you can see minus half plus 1 equal to 0, and for sigma V it's 1 plus minus 1 plus 1, which is equal to 1. The matrices for sigma V dash and sigma V double dash are a little bit more difficult, but as we shall show, the characters for sigma V dash and sigma V double dash are all the same because they belong to the same class. From the matrices we can, as before, develop the multiplication table for C3V as shown here. Note that sigma V times sigma V dash is equal to C3 squared, whereas sigma V dash times sigma V is equal to C3. Similarly, C3 times sigma V is equal to sigma V dash, whereas sigma V times C3 is equal to sigma V double dash. Thus, from the multiplication table, it is evident that C3V is not an abelian group. Thus, there will be classes of order greater than 1. There can be classes of orders 2 and 3, since 2 and 3 are both integer divisors of the order of the group, which is 6. It can again be verified from the multiplication table that the classes in C3V are identity, which forms a class by itself, C3 and C3 squared, which form another class, and sigma V dash and sigma V double dash, which form yet another class. We will write these as I 2C3 and 3 sigma V. We will stop here for today, and next time we will talk about the great orthogonality theorem and show how group theory can be used to derive the selection rules for spectroscopic transitions. See you next time.